Here is a question. Read it carefully and think about the answer. Let us solve it step by step. Let us begin solving this step by step. The starting material is a ketone hydrazone derivative. Specifically, it is the N-methylene to phenylethyl hydrazone of cyclohexyl butyl ketone, the ketone being 1-cyclohexyl 1-butanone, i.e., cyclohexane with a propyl group attached to a carbonyl carbon which also bears a cyclohexyl group. The imine nitrogen carries a methyl group and an NH, CH to CH to pH chain, making it a Shapiro type or Bamford-Stevens type substrate. Moving on to the next step. Treatment of a hydrazone, specifically a tosylhydrazone or similar, with a strong base like LDA leads to the Shapiro reaction. LDA deprotonates the NH of the hydrazone to give the lithiohydrazone anion. A second equivalent of LDA deprotonates alpha to the C is equal to N to generate a vinyl carbanion, vinylithium, via elimination of N2. The loss of N2 gives a vinyl carbanion intermediate. Moving on to the next step. N2 is lost, consistent with Shapiro reaction, and PHCH is equal to CH2 styrene is produced. The PHCH is equal to CH2 comes from the NH, CH2 pH portion. After loss of N to the vinyl anion can abstract or the beta elimination of the PHCH to CH2 portion gives styrene, via E2 type elimination from the NCH to CH2 pH group as the nitrogen leaves. This confirms Shapiro type fragmentation. And for the final step. The ketone is cyclohexyl propyl ketone, cyclohexane C is equal to O, CH to CH to CH3. In the Shapiro reaction, the C is equal to N becomes C is equal to C after loss of N2 and protonation, or the vinylithium is protonated. The double bond forms between the original carbonyl carbon and the alpha carbon of the butyl chain, the CH2 adjacent to C is equal to N. This gives cyclohexane CH is equal to CH, CH to CH3, i.e., cyclohexyl group attached to a carbon bearing a double bond to the next carbon, with an ethyl group on the far end, cyclohexyl CH is equal to CH, CH to CH3. In the Shapiro reaction with two equivalents of strong base, LDA, the less substituted, more kinetically accessible, vinylithium forms and upon protonation gives predominantly the Z or E alkene depending on conditions. With LDA, to equiv, the Shapiro reaction gives the less substituted alkene with defined geometry. The product is cyclohexyl, methylene connected via double bond, specifically cyclohexyl, CH2CH is equal to CH, CH to CH3, weight, re-examining, the ketone carbon is the one bearing cyclohexyl and the propyl chain. So C is equal to N is at that carbon. Loss of N2 gives vinyl anion at that carbon, CYC dash is equal to no. The vinylithium is CYC is equal to CH, between former C is equal to O carbon and alpha carbon of propyl. This gives CYCH is equal to CH, CH to CH3 after protonation, if 1H is available, or CYC is equal to CH, CH to CH3, still attached to cyclohexane. The product is cyclohexane ring with substituent, CH is equal to CH, CH to CH3 attached via a CH2 matching option A, which shows cyclohexane CH2 CH is equal to CH, CH to CH3 with Z configuration. Option B shows an exocyclic double bond, butylidene directly on ring, which would arise from a different connectivity. Option C shows E configuration of the same carbon skeleton as A. Shapiro with LDA gives Z-alkene preferentially. Option D shows a terminal alkene, which is not consistent with internal double bond formation. The Shapiro reaction with the given substrate gives the Z-internal alkene as in option A. Therefore, the correct answer is A. Therefore, the correct answer is option A.